Hello, and welcome to the next section of our Chapter 9. I know we're skipping around a bit, but that's because we want to focus on a few specific scenarios about when we use our significance tests. So there's lots of different kinds of significance tests because last time you saw when you wrote hypotheses, sometimes your problem talks about proportions, sometimes it talks about means, and sometimes it could be even more different scenarios. So we're just going to pick a few to focus on because we're not trying to cover a whole bunch of them. So in this section, we are talking specifically about averages or means in the problem. So we're making a claim about an average of some sort. So we talked about the different steps that we want to follow in a significance test last section. So in general, we're always going to state the hypotheses. We talked about how to write the HO and the HA. The second step is to check conditions. So that's something we're going to talk about this section. We're going to find the test statistic and find the p-value. So last time we talked about what the p-value was, but we didn't actually have to calculate anything. It was always just given to us first. So now we're actually calculating it. So the test statistic and the p-value goes together. It's like the calculations necessary in order to calculate that p-value, the probability. And then finally we make a decision, which we did last time. So let's talk about the conditions. In order for a significance test to actually work and be conclusive, we need a couple things. We have to have random samples. So our data that we collected when we calculated the mean from our sample or the standard deviation from our sample has to be a random sample that we got it from. The other condition we need is that we need normal distributions. So in order to do our p-value, to find our p-value and our test statistic, we can't calculate probabilities without that normal curve, so that's why we need normal distributions. To obtain that, we need our sample size to be greater than 30. So this comes from the central limit theorem. The central limit theorem is a theorem that says the larger sample sizes you have, their sampling distributions are going to be approximately normal. So that's why we need large sample sizes. So after we check our conditions, then we can find our test statistic. So our test statistic is just a formula that we use. You're basically looking for like a z-score. Back when we did our normal curve probabilities, you had to find a z-score first, and then you used a table to find your probability. So our test statistic has this special name because it's a significance test, and we're finding a z-score for that significance test. So it's called a test statistic. It's not quite a z-score because we are not using the actual z-score table or the actual normal curve. When we're dealing with averages, there's actually a different distribution that we're going to use. So this is called the t-distribution. It's very similar to a normal curve, but it changes its shape depending on your sample size. So the bigger your sample size, like we said, we want that normality, we want big sample sizes. The bigger your sample size, the closer the shape looks to normal, like a regular bell-shaped curve. When your sample size is smaller, then the bell-shaped curve is actually like kind of flatter, like if you imagined the normal curve but you like squished it a little bit. So like the ends kind of pop out more, kind of a squished shape. But it really doesn't matter for us as much. We really just need to know how to find the test statistic, how to use the table to find the p-value. So the formula for the test statistic looks like this. In this formula, x bar is our sample mean. So this is the mean from our sample minus mu. So remember, mu is what we used in our hypotheses. So whatever number you used in your HO and HA, that's what goes there. Then you divide by the standard deviation of the sample divided by the square root of n, where n stands for your sample size. So once you plug in all your numbers and do the formula, that number is what you're going to use to find the p-value in the table. So to find the p-value, our p-value, we're going to draw pretty much a normal curve. So right in the middle of the normal curve is always going to be 0. So because we're dealing with the t-score instead, it's not the regular mean and standard deviation that we're labeling. So it's just going to be 0 in the middle. And then whatever number your test statistic you got was, whether it's negative or positive, that's where you're going to put it on the left or the right, because negatives would go on the left, positives would go on the right. And then we're going to shade our normal curve based on your HA. So if your HA was a less than symbol, you would shade to the left. If it was a greater than symbol, you would shade to the right. If it's not equals, you would actually have to shade both sides. So wherever your number was, you would shade that side and then shade the other side as well. You're always shading towards the outsides of the graph, never towards the middle. Once you have that, then we're going to use our calculator to find our p-value instead of using a table. So it's actually easier for us. We have the technology, so we might as well use it. On the calculator, these are the buttons that you're going to press. So let me pull up my calculator so that we can do this together once we have numbers below. But these are the instructions. So in second vars, you're going to choose number 6. It's titled TCDF. This is where you input your test statistic number that you got from doing your formula. And then you're also going to have to type in something called a DF, which stands for degrees of freedom. Degrees of freedom, so earlier I said that t-distribution is based off of your sample size, and that's what degrees of freedom are. So based off of your sample size, we calculate the degrees of freedom by doing n minus 1. N being your sample size, and then we subtract 1 from it, and that would be your degrees of freedom. So let's do an example. According to the Animal Diversity Web, adult golden hamsters have an average weight of 4 ounces. To test this claim, an animal researcher selects and weighs a random sample of 30 golden hamsters. The mean weight is 4.033 ounces with standard deviation 0.199 ounces. The researcher wants to perform a test at the alpha equals 0.10 significance level. Is there convincing evidence that the mean weight of adult golden hamsters is actually greater than 4 ounces? So we're going to do the entire significance test here. So let's write our hypotheses first. So this problem, we're talking about hamster weight. It claims there's an average weight of 4 ounces. So we know 4 is what we're using in our hypotheses. It's an average, so we know we are going to be using the symbol for mu. And then in the question, it says, is there convincing evidence that the mean weight of golden hamsters is actually greater than? So greater than, we know our HA is going to be greater than then. All right, so there's our hypotheses. Our next step is to check our conditions. So we have 2 to check for. We wanted things to be a random sample and normally distributed. So random sample, it does say in the problem right here that it's a random sample. So we can say that's given to us. And then for normality, we're checking that sample size has to be greater than 30. So we have a sample of 30 golden hamsters. That counts as greater or equal to 30. So we do have large samples here. Alright, so now let's calculate our test statistic. We're using this formula, and we need to identify all the pieces that go along with our formula. So our sample mean here, they told us the mean weight is 4.033 ounces. Mu is the 4 that we use in our hypotheses. The standard deviation, they gave us 0.199, and root n, so n is our sample size, so we're using 30 there. So let's plug that into our formula. So when I plug everything in and calculate this out, I get 0.9083. Alrighty, so then I'm just going to fill out the rest of this box here. They told us alpha was going to be 0.10, because they told us that in the problem over here. And then let's calculate our p-value. Okay, so here's my normal curve with 0 in the middle. The number that I got for my test statistic was positive 0.9083, so that goes on the right side of my normal curve since we have a positive number. It's bigger than 0. And then we're shading to the right because our HA, we were using the greater than symbol, so we know to shade to the right. I kind of think about it as like whichever way the arrow is pointing, that's the direction you're shading in. Okay, so now let's use our calculator to actually calculate this probability here. So we're going to go second vars. You're looking for TCDF number 6 right here. So I'll hit number 6. So if you have an updated calculator, these are the things it's going to give you. This really stands for like the negative 100,000 that we wanted. So if your calculator is old school and just gives you the parentheses, then you're typing in with these numbers just separated by a comma. Upper is going to be your test statistics. So we got 0.9083. And then our degrees of freedom is what we have to input here. So degrees of freedom, remember the formula was n minus 1. So our n was 30, minus 1 would be 29. Then you're going to scroll down to paste, enter one more time. That's our p-value. If we round to 4 decimal places, we get 0.8144. However, remember with normal curves, when you're shading to the right, there's an extra step that you have to do because all the p-values that we ever get from our calculator are always going to give us what's to the left. So in order to get what's to the right, we need to subtract by 1. So really, we want to find 1 minus this number. When I do that, I get 0.1856. So our p-value is like 18.56% as a probability. Alright, now that we have our p-value, remember our goal is to compare this with our significance level. So we said alpha was 0.10 here, and so we're comparing to see if our p-value is smaller or greater than the 0.10. 0.18 is bigger than 0.10, so if the p-value is bigger, this is when we fail to reject. For our conclusion then, so since we fail to reject our HO, that means we do not have convincing evidence that the true mean weight of golden hamsters is greater than 4 ounces. So remember, if we fail to reject HO, that means we can't prove that HA is true. So that's why we do not have convincing evidence. And then we write whatever our symbols meant in words, that the true mean weight of golden hamsters is greater than 4 ounces. So that's a full significance test right there. We do the hypotheses, the conditions, find the test statistic, use that to calculate our p-value, and then we compare our p-value and the alpha level to then make our conclusion. So I want to do one more example with you where the information that were given to us is slightly different. So in this example, rather than just telling us what the mean and standard deviation is, they actually give us the data. So in this case, it's talking about sub sandwiches. However, they notice the lengths of the 6-inch sub sandwiches that they get at their favorite restaurant seem shorter than the advertised length. To investigate, they randomly selected 24 different times during the next month and ordered a 6-inch sub. Here are the actual lengths of each of the 24 sandwiches, and here's their data that they got. Do these data give convincing evidence at the 0.10 level that the sandwiches at this restaurant are different than advertised on average? So, if we go through our data here and do our whole hypothesis test, then we can figure out if we have the convincing evidence or not. So let's start with our hypothesis. Alright, so the claim here is that the restaurant is claiming that these subs are actually 6 inches long, and so that should be our number that we're using for our hypotheses. And we are dealing with the average length, so we know we're going to use mu. And then finally in the question it says, do these data give convincing evidence that the sandwiches at this restaurant are different than advertised on average? So they didn't say anything about less than or greater than, so that's how we're going to know that in this problem we're going to use a does not equal sign, so that this actually makes it a two-sided test. So here's my hypotheses, and then we move on to check our conditions. So they did tell us that in this problem that each of their sandwiches were randomly selected, but then if we look at our sample size, we used 24 different times to get the 24 sandwiches. 24 is not a big enough number for our sample size to be greater than 30. So, if we don't have a big enough number, then we have to do what's like the second best way to check for normality. We want to see if the graph of these data is super skewed to either the left or the right, or if there's any outliers. So there's a quick way to do that in the calculator. So the first thing we want to do is type in all our data into L1. So remember, to get to L1, you hit the stat button, then enter, and then you can start typing things in. So let me do that really quick. Alright, so I've got all my data points typed in. Hopefully you did it correctly. To make our graph, we want this button here in blue where it says stat plot. So since it's blue, we're going to go second, that button. And then we want to actually plot it out on here. So we're going to hit enter to choose one of the graphs. We want to make sure it says on. And then we're going to choose the box plot right here. So see, there's two box plots. One of them has dots at the end, so the dots tell us immediately if there's going to be outliers or not. So the calculator calculates for outliers using the outlier formula. The other box plot does not calculate outliers for you, so we don't want that one because we want to be able to see whether our graph is going to be skewed and has outliers. So hit enter to make sure you pick that graph. X list, this is where we have all our data, so L1, and then everything else stays the same. So let me go back out into my home screen, and then I'm going to hit zoom number 9 to make sure that it fits my data and makes my graph nice and pretty. So here's my graph of all the data that I entered. So we are looking for extreme skew. We don't see any because if it was super skewed, either side of your whiskers would be a lot longer than the other. We don't really have that. We see the right side is a little bit longer than the left, but not by a whole lot, so we don't count this as extremely skewed. And that's good enough for us. All right, so I've drawn a quick sketch of the graph that I saw in my calculator, and then I'm going to say there's no extreme skew, no outliers, so we keep going with our problem now. So let's find our test statistic and our p-value. To plug into our formula, we're actually going to need to figure out what the sample mean and sample standard deviation is, because that's something that wasn't given to us. But then we do have the data, so we can calculate that ourselves. In order to find that in the calculator, we're going to go back to our home screen, and then to calculate everything really quickly, we want stat, go over to calc, and then the first one var stats. Our list should say L1 because that's where all our data is. Everything else stays blank. Hit calculate. Remember, the first number is your mean, so x bar, just like our formula. So 5.68 if we round to 2 decimal places. Our standard deviation is the one that says SX. So that's our standard deviation of our sample, so 0.657 or 0.66. But just so that we are as accurate with everything as possible, we're going to use 4 decimal places for everything. So rounding my mean to 4 decimal places, I get 5.6771 minus our mu, which was 6 in our hypotheses, divided by our standard deviation, which was 0.6572 if I round to 4 decimal places, over the square root of our n being 24 because we had 24 data points here. When I do that, I get negative 2.4070. Our alpha level in this case was 0.10 again. Since our test statistic was a negative number, this time it's going to go on the left side of 0. So that would be where negative 2.4070 is. And then to shade, we're basing this off of our HA. So our HA we said not equal to. Not equal to means that this is going to be a two-sided test, so we actually have to shade both sides. So from this number to the left, and then also on the right side as well. Okay, so our original though is the one that's on the left. So when we use our calculator to calculate TCDF, we're going to go second bars, number 6. The upper is going to be negative 2.4070. Our degrees of freedom here, our sample size was 24. Minus 1 will be 23. Paste. Okay, so from here it's saying from our left side and everything from the left of negative 2.4070, that probability is 0.01225. Something. If we want both sides, since it's going to be symmetric on both sides, all we have to do is multiply our probability by 2. So anytime you have a two-sided test where your alternative hypothesis is not equal, your p-value needs to be multiplied by 2. So times 2 gives me this number. So that'll be my p-value. And finally, we take our p-value, compare it with our alpha level. So 0.02 is smaller than 0.10. So for our conclusion, because our p-value is low, we get to reject the HO. It's a nice little rhyme to remember that by. So we are rejecting HO here. If we reject HO, then we do have convincing evidence that, and then that means our HA is true, that the sandwiches at this restaurant are different than advertised. They are not equal to 6. So that's our full hypothesis test. So if they give you data instead of like just telling you the mean and standard deviation, then you'd have to calculate your own in order to do your test statistic. Also, if your sample size is not big enough, you have to make a graph. Otherwise, everything else for two-sided tests, you want to remember to multiply by 2 for your p-value. Otherwise, your p-value will not be correct. All right, that's it for this section. Thanks so much for watching. See you next time. Bye.